Subscribe to our YouTube channel and press the bell icon to get the latest updates.
The advanced LIGO detectors have detected gravitational waves from the merger of a black hole and a mysterious object whose nature astrophysicists have not been able to determine still. The gravitational wave signal from this merger event came from 800 million light years away, and the observed event is described by the LIGO teams as being very loud. It is in fact the third loudest event observed to date. The one thing we know is that the masses of the two objects that inspiraled and merged was so different that this is the most asymmetric collision that we've ever observed. In this video, we'll talk more about this collision, what the mysterious object that smashed into the black hole could have been, and why this particular event is so perplexing and confusing. My name is Sandhya Ramesh, and this is Pure Science. Before we go into the details of this finding, let's first examine what gravitational waves are and how they're formed. Gravitational waves are disturbances in the fabric of space-time that radiate outward when two large masses spiral inwards towards each other or collide, and the waves travel at the speed of light. A simple way to visualize this would be ripples on the surface of still water once you drop a pebble into it. When gravitational waves propagate through space-time, they bend and twist space around us, and this is the principle we use to detect these waves. There are two advanced LIGO observatories in the US and one in Italy called Advanced Virgo. But all of these observatories have people and scientists from all over the world working on the data that they generate. The observatories are constructed to have an L-shaped structure with two arms extending outwards up to 4 kilometers perpendicular to each other. At the point where the arms meet, there is a beam splitter that sends light through the two arms. The light bounces off a mirror at the end of each of these long arms and then comes back to the source. Because gravitational waves bend space, which then ends up stretching in one direction and compressing in the perpendicular direction, the light waves that come back do not meet at the exact same time when a gravitational wave passes through the interferometer. We can then use the difference to calculate how far away the waves originated from and what kind of bodies caused the gravitational wave. Having multiple interferometers around the world helps us triangulate the location of the gravitational wave merger event more precisely. Gravitational waves are usually caused by rapid acceleration or collision of what are known as compact objects. In astronomy, a compact object is a stellar remnant that is left over after a star dies. There are three kinds of compact objects: white dwarfs, neutron stars, and black holes. These compact objects are called so because they have a very high density. That means that per unit volume, the mass they hold is enormous. White dwarfs are no more than 1.44 times the mass of the Sun or solar mass, but their radius is just about 2% the radius of the Sun, about 13 to 14,000 kilometers. Sometimes the radius can even be as small as the radius of the Earth, around 7,000 kilometers. Neutron stars have a maximum mass of about 2.4 times the mass of the Sun, but are typically about just 10 kilometers in radius, thousands of times smaller in size than a white dwarf, and thus are much more dense. Black holes work slightly differently. Nothing escapes a black hole, not even light. Everything that gets sucked into a black hole gets sucked into a singularity where the laws of physics completely break down. So the singularity is essentially just a point with infinite mass that sucks anything that comes near it. Structurally, black holes have an outer boundary called the event horizon. If something including light falls into the event horizon, it cannot escape and will get sucked in. The radius from the singularity point to the event horizon is called the Schwarzschild radius, and this is considered to be the radius of the black hole. Schwarzschild radius is proportional to the mass of the black hole. The more mass a black hole adds, the larger its radius. There is currently an unknown critical threshold for black holes, but the smaller ones are thought to be somewhere around 3 times the mass of the Sun, and black holes can actually go on to contain as much as millions to billions of times the solar mass. One of the smallest black holes we know contains just about 3.8 times the mass of the Sun, but its radius is only 12 kilometers. If the Sun itself were to be replaced with a black hole with the same mass, its radius would be just 3 kilometers. On the other hand, there is a supermassive black hole in the center of the Milky Way galaxy called Sagittarius A star, around which our entire galaxy revolves. This black hole has a mass of approximately 4.1 million solar masses, but its radius is just 7 billion kilometers, or a little over the distance between the Sun and Pluto. Now that we understand the sizes and masses of these compact objects, we come to the mysterious object that caused the gravitational wave under discussion. The black hole that collided with this object was 23 times the mass of the Sun, which was consistent with other black holes that LIGO has observed gravitational waves from. But the lighter object is determined to be between 2.5 and 3 solar masses. The heaviest neutron star that we know is 2.4 solar masses, and the lightest black hole we know is 3.8 solar masses. This means that the mysterious object is either the heaviest neutron star we know or the lightest black hole we know, and sits right in this mass gap that we are unfamiliar with. This means that even the origin of the object is now a mystery, because we do not have maths to explain what sizes of stars can collapse and form an object that has a mass in this range. The mass discrepancy of the two objects is in a 9:1 ratio, making this the most asymmetrical collision that we've observed. The event is called GW 190814, meaning it occurred on the 14th of August in 2019 UTC time. Additionally, when neutron stars collide, they fling matter outward and thus produce electromagnetic radiation and light, which can then be seen by telescopes on Earth after the detection of a gravitational wave. It is often referred to as the afterglow of the merger. When black holes collide, on the other hand, there is usually no light that's emanated. This collision also did not produce any light, and we think there could be multiple reasons for this. One is that the collision occurred 800 million light years away, so maybe it's just too far for us to detect light from it. Or maybe the collision was between two black holes, in which case we know that there would be no light. If the mysterious object is a neutron star, maybe the larger black hole simply completely swallowed the smaller neutron star, again not emitting any light. Ultimately, we don't yet know. Because the mathematics that we are familiar with does not allow for neutron stars to be this heavy, we think that this could be the lightest black hole we know. But we can't discount the fact that it could be a neutron star, in which case our mathematics and understanding of stars of these sizes and masses is wrong and needs to be completely re-evaluated and reformulated. One way or another, this gravitational wave has changed our understanding of the universe significantly. If you like this video, please consider contributing to ThePrint. You will be able to do so at theprint.in/contribute. Every single bit helps. Thank you for watching this video.